In this section 10.4, we're going to be defining our inverse trig functions. Before we do that, let's just review some properties with inverse functions. So here, remember when we talk about an inverse function, that just means that for every x value, there's exactly one value. So all the ordered pairs are unique. If a function is one-to-one, so that means it passes the horizontal line test, then it does have an inverse. When we talk about inverse functions or functions that are inverses of each other, what we're actually doing is exchanging their domain and their range. So remember, the domain is going to be the x values and the range is the y values. So you're just exchanging x and y values. If we have a graph of a function that does have an inverse, then its inverse function graph is going to be a reflection across the line y equal to x. And we kind of talked about this in number 3, but if a point AB is on the function, then the point BA is on its inverse. We also have this canceling property. We have to be careful when we use this property with trig functions because trig functions aren't one-to-one. So typically, if you have a one-to-one function and you have its inverse when you compose them, whatever x you put in is the x that you get back out. So a function and its inverse will cancel, and it doesn't matter the order that you compose. It could be the function with its inverse and the inverse with its function. They will cancel each other out. Whatever x you put in is the same x that you get out, so they undo each other. But again, we have to be careful with trig functions because they're not one-to-one, and we'll talk about that some more in a bit. And then remember, if you wanted to find an inverse function and you have a function, then you would place the f of x with y, and then change your x and your y values, solve for y, replace y with inverse notation. Let's just do a little bit of review with that. We're first going to look at a graph of an inverse function, and then we're going to find an inverse function algebraically. So here I have a graph of some function. I'll call this function f. And I'm going to pick some nice points on f so that I can graph its inverse. I'm going to look at the ordered pairs x and y. I can see that this graph passes through the point 1, 0 and 2, 1. So those are some nice points. What about 4, 2? And then if I go in the other direction, 1/2, -1. I think that's going to be enough for me to graph the inverse function. So now I'll use a different color for that. Let's use red. So I'm looking at the inverse function, and remember that -1 is not an exponent. It's inverse function notation. So all I have to do to graph the inverse function is exchange x and y from my function. So if my function passes through 1, 0, inverse passes through 0, 1. 2, 1 becomes 1, 2. 4, 2 becomes 2, 4. And then half -1 becomes -1, 1/2. So I have enough points to draw my inverse function. It's going to pass through 0, 1, 1, 2, 2, 4, -1/2. I'm going to connect these dots. And to match up with my function, I'm going to add little arrows at the end. Now notice that the inverse function just runs along that x-axis, but it never touches or crosses because it is actually a reflection about the line y equal to x. So these are mirror images of each other, flipped over that diagonal y equal to x. So that's how you would graph an inverse of a function. You would just get some points, exchange the x and y, and then graph. So just as a review, if you had a function and you knew it was one-to-one and you had to find its inverse, then the steps are replace the f of x with y. So in example 2, my function, which is one-to-one, is 2x minus 7. I'm going to replace f of x with y. And then to find an inverse, remember we're just exchanging our x and our y values. So this becomes x equal to 2y minus 7. And now I just want to solve for y. I'm going to add 7 to both sides. And then I'm going to divide by 2 on both sides. Replace y with my inverse function notation. So f inverse of x is going to be equal to x plus 7 over 2. Now you have a single number 2 in the denominator, so if you would prefer, not necessary, you can break this up into 1/2 x plus 7/2. So you might notice that this is actually a line is written in y equal to mx plus b form. My original function f was also a line written in y is equal to mx plus b form. So if you have a line and it has an inverse, its inverse will also be a line. So now let's look at our inverse trig functions and we'll define those. The problem is, and we'll look at the sine function first. So the problem is, if you look at this sine function graph, you can see that it's not a one-to-one function. It doesn't pass the horizontal line test. So what we're going to do is we're going to temporarily restrict our sine function. And then here, I don't want to do that. I want a darker color. Here, I'm going to restrict sine function temporarily. So I get all these negative values and I get all the positive values, but nothing repeats. So they're all unique points. Now remember that was in our number 1 for every x value, there is exactly one y value. So that's what it means, nothing repeats. So if I temporarily restrict from negative pi over 2 to positive pi over 2. And just look at that piece. That piece is one-to-one. It passes the horizontal line test, so it does have an inverse. So to find its inverse, I'm going to just find some points. This first point here is going to be the point negative pi over 2, comma negative 1. And the next nice point that I see is the point 0, 0. And then this last one here is going to be pi over 2, comma 1. So I have these 3 points. I'm going to exchange them, and then those would be the points for my sine inverse. That would be these 3 points here. So the negative pi over 2, negative 1 becomes negative 1, comma negative pi over 2. 0, 0, if I flip it, it's still 0, 0. And then pi over 2 comma 1 becomes 1 comma pi over 2. And this is sine inverse. Now here's some properties with our inverse sine function. If y is equal to sine inverse of x, and then sometimes that negative 1 gets a little bit confusing because people think, oh, that's an exponent. So remember, that's not an exponent, that's inverse notation. So if you get confused, you can also use this other way to describe an inverse trig function. So for sine, we can also call it arcsine of x. So feel free to use either the sine with that negative 1 or the sine inverse or arcsine. They mean the same thing. So if you do have y equal to sine inverse of x, what that means is that sine of y has to equal to x. So oftentimes if we're not using a calculator and we want to find the value of an inverse trig function, we rewrite it so that it is not the inverse trig function, it's the original function. that we restricted. So the domain of our sine inverse, remember we're switching the domain and range from sine, but it's a restricted, right? To flip it, and it becomes, the range becomes the domain becomes the range of our restricted sine function. So our restricted sine function, the x values went from negative pi over 2 to pi over 2. So that was the domain of my restricted sine function. So that becomes the range of sine inverse, negative pi over 2 to pi over 2. So remember the brackets here, that just means that it includes the endpoints negative pi over 2 and pi over 2. Now the range of my restricted sine function was negative 1 to positive 1, so that becomes the domain of sine inverse. So something that you really need to be able to do is you need to be able to switch from the inverse to the sine function. So imagine if I were to take sine on both sides of this equation. So I'm just sining both sides of the equation. Notice that on the right-hand side, the sine and the sine inverse would cancel from one of my inverse properties, and this just becomes sine of y equal to x. So again, and this is similar to what we did with log functions. We switched from the log form to the exponential form because the exponential form oftentimes was easier to work with, easier to graph, and so on. So we'll do that with these trig functions as well. If we're not using a calculator, we will switch from the inverse notation to the regular function notation. Just remember that it was a temporary restriction on the sine function. So once we actually do look at the sine function again, it's going to be the whole function, not just that restricted piece. We only temporarily restricted it so we can define an inverse trig function. In example 3, it says find the exact value but do not use a calculator. So this is y equal to sine inverse of 1. So without a calculator, I can just write this as sine of y equal to 1. And then ask myself, okay, when is sine equal to 1? Well, sine is equal to 1 at pi over 2. But remember, there's infinitely many values where sine is equal to 1 because it's actually not a one-to-one function. It goes on forever and ever in both directions. So if I were to go one circle around again on the unit circle and add 2 pi, I would get 5 pi over 2. Sine of 5 pi over 2 is 1. If I went in the negative direction, negative 3 pi over 2. And there's infinitely many values where sine is equal to 1. So what we want to do is we want to choose the value that is in the range of sine inverse. So going back to the range of sine inverse will only give us values from negative pi over 2 to pi over 2. So I'm going to choose pi over 2 and not the other ones. And that's the tricky part when you're dealing with inverse trig functions, knowing which value actually works. So you do need to know the ranges for all of your trig functions, inverse trig functions, sorry. Well, let's try this again in B. We have y equal to sine inverse of negative square root 3 over 2. So to solve that without a calculator, we need to find sine of y equal to negative square root of 3 over 2. So we have to ask ourselves, okay, when is sine equal to negative square root 3 over 2? And it's negative, so I know it's going to be, if you're looking at your unit circle, that's going to be quadrants 3 and 4. So I think 4 pi over 3. And then 5 pi over 3, that would be quadrant 4. And then there's a problem, because remember, this is sine inverse. It's going to give me y values between negative pi over 2 and pi over 2. These two values are not within the range of sine inverse. So when you look at the range of sine inverse, since it goes from negative pi over 2, if you look at the unit circle and you start with negative pi over 2 and you go up to 0, that would be like quadrant 4. And then when you go from 0 to pi over 2, that's quadrant 1. So you're looking at values from quadrant 1 and quadrant 4, but negative values. Again, looking at this graph, right? We have negative values between -1 and 0, and it's going to give me back y values from 0 to negative pi over 2, and then from 0 to 1 we get y values from 0 to positive pi over 2. So you always have to make sure that the values are within the range of, in this case, sine inverse. So that means we're actually going to, if you're looking at the unit circle, we're going to go in the opposite direction. We're going to go from 0, we're going to go down to negative pi over 3. And that's within the range from negative pi over 2 to positive pi over 2. So these first two are not going to work. It's this last value. So sine inverse of negative square root 3 over 2 is equal to negative pi over 3. Okay, you can check with a calculator on this just to double check. Now, what if we were composing sine and sine inverse? Well, normally, if sine was 1 to 1, if we composed it with its inverse, then all we would have to do is cancel them, and that would be equal to 1. What you put in is what you get out. But remember, sine was only temporarily restricted. It actually is not a 1-to-1 function, so instead of using the canceling properties in this case, I'm going to evaluate this separately. I'm going to first look at, now remember, we're composing functions. We have sine inverse inside of sine. So whenever you do a composition of functions, you always work from the inside out. So I'm going to let this be a y value. And then look at this as y equal to sine inverse of 1. And we actually did this in part A. We already figured out that that was pi over 2. But just as a review, so this would be sine of y equal to 1, which means y has to be pi over 2, because pi over 2 is within the range of sine inverse. So now our sine function becomes sine of pi over 2. And that's simply 1. So in this case, we could have simply canceled sine and sine inverse and just had 1. However, that's not always going to be the case. It depends on what you're actually putting into these composition of functions. So my advice is, whenever possible, do it in pieces. So sine inverse composed with sine of pi, you would think that, oh, cancel it, it's equal to pi. But it's not, because remember, sine inverse can only give us values from negative pi over 2 to positive pi over 2. Pi is not within that range. So again, do it separately. Sine of pi, that's 0. So this becomes sine inverse of 0. And that's going to be equal to some y value. So that sine of y is equal to 0. So when is sine equal to 0? Well, that would be when y is equal to 0, or pi, or 2 pi, or negative pi, and so on. But here 0 is a value that is between negative pi over 2 and pi over 2. So notice that we couldn't just simply cancel sine inverse and sine and have it equal to pi, because this is actually equal to 0. Now cosine is going to be the same as the sine function. Again, cosine is not 1 to 1. It does not pass horizontal line tests. So we're going to restrict it so that we get all the cosine values from -1 to 1, but nothing repeats. So a logical place for us to do our restriction is from 0 to pi. And then this one piece of cosine gives me all values from -1 to +1. And with that restriction, we will define our cosine inverse function. So let's get our points. We have the point 0, 1. And then we have the point halfway between would be pi over 2, comma 0. And then at pi, we have -1. So I'm going to take those values and flip them to get my cosine inverse function. So 0, 1 becomes 1, 0. And pi over 2, 0 becomes 0 pi over 2. And then pi -1 becomes -1 pi. So exactly the same as what we did with sine. We're just looking at different values. Now, if you look at cosine, we're looking at value, or we're looking from 0 to pi. So you can kind of think of that as like quadrant 1 and quadrant 2. So cosine is positive in quadrant 1, negative in quadrant 2. So we get all the positive and negative values. Now, when we look at cosine inverse, or arc cosine, to evaluate it without a calculator, we would evaluate cosine of y equal to x, so exactly the same process as we did with sine. Domain is -1 to 1, but the range is that restriction we had on cosine from 0 to pi. So now cosine inverse will only give us y values back that are within 0 to pi, and including 0, including pi, because it's a bracket, not a parenthesis. We'll go and do the same thing we did with sine. If I wanted to evaluate y equal to cosine inverse of 1 without a calculator, I would evaluate cosine of y equal to 1. So when is cosine 1? Well, cosine is 1 at 0, 2 pi, -2 pi, and so on. However, with cosine inverse, we're looking at values between 0 and pi, including 0 and pi. So we would choose 0. These other values will not work. Let's do this again in B. Cosine inverse of -1/2. So remember, 0 to pi, our range, we're looking at quadrant 1, quadrant 2. So if I'm looking at a -1/2, that tells me I'm going to have to get something back in quadrant 2, because that's where cosine is negative. I'm going to rewrite this as cosine of y equal to -1/2. And in quadrant 2, cosine is -1/2 at 2 pi over 3, I believe. And I could stop there, because I know 2 pi over 3 is a value between 0 and pi. However, you know, cosine of y is also, or cosine is negative also in quadrant 3, and in that case it would be 4 pi over 3. But since 4 pi over 3 is too big, it's outside of the 0 to pi range, 2 pi over 3 would be my answer. Now again, if we compose cosine with cosine inverse, it would be nice if we could just cancel and get -1. And sometimes it does work, sometimes it doesn't. We saw that with sine, same thing with cosine. In this case, it actually does equal to -1. They do cancel each other out. But let's go ahead and evaluate the inner, which is cosine inverse of -1. So I'm going to set that equal to some y value. So I have y equal to cosine inverse of -1. So cosine of y, when is that equal to -1? So cosine is equal to -1 at pi. Oh, and pi is within the interval 0 to pi. So I could stop there. But you know, negative pi also works, -3 pi, +3 pi, but those values are not within our range of 0 to pi. So we are going to replace the cosine inverse with pi, and now we're just evaluating cosine of pi. And we know cosine of pi is equal to -1. So in this case, canceling cosine and cosine inverse did work, but not always. So we do have to be careful with that. So can I cancel and have this equal to pi? In this case, it actually does work. But let's do it in pieces. Cosine of pi is -1. So we're evaluating cosine inverse of -1. And we actually did evaluate that in C, but let's just go ahead and set that equal to some y value so that cosine of y is equal to -1, just to practice. Do it again. Cosine is -1 for pi, and I could stop there because pi is within the 0 to pi range. Okay, the next one we're going to look at is tangent. So as we can see, clearly it's not passing horizontal line test. It does have asymptotes though. So what we're going to do is a logical restriction on tangent would simply be between the asymptotes -pi/2 and pi/2, and we'll just be looking at this middle portion here as our restriction on tangent. That restriction is 1-to-1. It has an inverse. And remember, since we're exchanging our x's and y's, we're exchanging domains and range with a function and its inverse. So since we actually have asymptotes as well, so here we have x equal to -pi/2 and x equal to +pi/2. Since we're exchanging x and y values, we're also exchanging our asymptotes. Instead of having x equal to -pi/2, it becomes y. So if you look at tangent inverse, we have y equal to -pi/2 would be one asymptote, and y equal to +pi/2. So again, we're flipping x and y, we're flipping asymptotes as well. So let's look at some nice points on tangent, the restricted tangent. Well, I could see right away that I'm going to pass through the point 0, 0. I'm going to get some other key points halfway between 0 and pi/2. That would be pi/4. So remember, at positive pi/4, tangent is 1. That's going to be a nice point. Let's see if I can squish this in. So it's pi/4, 1. And then going to -pi/4, that's going to pass through -1. Maybe I will put a little arrow there. -pi/4, -1. So I have some nice points. I can go ahead and flip those to graph tangent inverse. It's going to pass through -1, -pi/4. So let's go to our graph, -1, -pi/4. Again, this goes on in both directions. I think I'm just going to put an arrow up here. -1, -pi/4. It's going to pass through 0, 0. And then at 1, it's going to pass through positive pi/4. Okay, so that's what the inverse tangent function looks like. What's really nice about tangent is when we do compose tangent with its inverse function, if the inverse tangent is on the inside and tangent's on the outside, the canceling property actually always works. And that's because of switching domains and range. If you look at the range for the restricted tangent, we're getting back values from negative to positive infinity. So that actually becomes the domain of our tangent inverse. It goes from negative to positive infinity. That means we could put anything we want into tangent inverse. Okay? It's going to give us back something from that restriction from negative pi over 2 to positive pi over 2. Notice that we do have parentheses because that's where our asymptotes are. And tangent is undefined at negative pi over 2 and pi over 2. So tangent inverse will not have range values there. So y equal to tangent inverse of x, or y equal to arctan of x, means that tangent of y is equal to x. So I'm going to do the same thing. Without a calculator, we would just rewrite it. Now with sine, it was negative pi over 2 to pi over 2 as well. Remember that was quadrant 1, quadrant 4 is what we were thinking about. So here this is going to be quadrant 1, quadrant 4 as well. So if we're putting in positive values into tangent inverse, we're talking about values coming back in quadrant 1. If we're putting negative values into tangent inverse, we're going to get values from quadrant 4, negative values. So let's look at A. We have tangent inverse of 0. That's going to be equal to tangent of y equal to 0. So when is tangent equal to 0? Just as a reminder, remember tangent is sine over cosine, which is a fraction. And the only time a fraction is equal to 0 is when the numerator is 0 and the denominator is not 0. So we get 0 over some non-zero number. That's the same as saying that sine of y has to be equal to 0. And now sine is equal to 0 at 0 and at pi and at 2 pi. But remember, we're looking for tangent inverse. Tangent inverse has to give us values back from negative pi over 2 to positive pi over 2, but we cannot include the negative pi over 2 and pi over 2. So the only value within that range would be the 0. Same thing we did with the sine function, sine inverse and cosine inverse would be the same thing we do for tangent inverse. We just have to be careful because tangent is a fraction of sine over cosine. Let's do this again with B. We have y equal to tangent inverse of 1, so that's the same as saying tangent of y is equal to 1. So when is tangent equal to 1? Well, tangent is equal to 1 when sine and cosine are equal, because this is sine of y over cosine of y equal to 1. If we multiply both sides by cosine to get rid of the fraction, we'll get sine of y equal to cosine of y. And sine and cosine are only equal when they're both square root 2 over 2 or both negative square root 2 over 2. So that would be in quadrant 1 at pi over 4. And I can kind of stop there because pi over 4 is within the negative pi over 2 to positive pi over 2 range. But also in quadrant 3, that would be 5 pi over 4. They're both negative square root 2 over 2, so they cancel and it's equal to 1. But the 5 pi over 4 is not in the range of tangent inverse, so it must be the pi over 4. Let's do some composition. Tangent inverse of tangent of pi. Well, if it were composed the other way around, if it was tangent of tangent inverse, then I could use that cancellation. But I can't do it here. what I have to do is I have to go in pieces. Tangent of pi, so that would be 0, which would mean tangent inverse of 0 is what I'm evaluating. We already did that, didn't we? We did that in part A. But just as a refresher, remember that's equal to some y value, so that tangent of y is equal to 0. Tangent is equal to 0 when sine is equal to 0, which would be at 0 and pi and so on. But pi is outside, so it must be 0. So notice that this is not equal to pi, this is equal to 0. Can't use the cancellation property there, but you can if you have tangent inverse on the inside. Because remember, tangent inverse, its domain is anything at all from negative to positive infinity. It's going to spit out a value, but then when we look at tangent, its domain is negative to positive infinity. So we could put anything in, tangent inverse, give us something, and then tangent would give us back, not domain, it's range, sorry, is negative to positive infinity. So because the domain of tangent inverse goes from negative to positive infinity and the range of tangent is from negative to positive infinity, it means that whatever you put in is exactly what you're going to get back out if you do tangent inverse first. So in this case, you can put this in a calculator and you will get 345. But basically, I can't do this in pieces because I really don't know what this is. Even if I wrote this as y equal to tangent inverse of 345, and then I wrote that as tangent of y equal to 345, I don't know what that is. So in this case, without a calculator, I can use canceling properties and say this is equal to 345. And the only reason why is because I can put in any number into tangent inverse, and tangent gives me any number back out. So a little bit hard to understand, but it may come up where you get some weird value going into the tangent inverse. So as long as it's tangent inverse first, tangent second, you can use the canceling property. When we look at the remaining three trig functions, we're not really going to spend a lot of time looking at the original graph and then graphing the inverse function. I'm just going to discuss the domain and range for cotangent inverse, secant inverse, and cosecant inverse, and then we'll take a look at the graph, but it's nothing that you have to memorize. As long as you can refer back to the domain and the range for these three and use them to select the correct values, then you're going to be fine. We'll go ahead and look at cotangent inverse first. So when we're looking at cotangent inverse or arc cotangent, we can rewrite it as cotangent of y equal to x, so exactly the same as what we did before. The domain of cotangent inverse is all real numbers from negative to positive infinity. So when you look at the graph, we have asymptotes at 0, and there's an asymptote, or at 0 and at pi. Sorry, I did that backwards. There's an asymptote at 0, even though the dotted line is not shown. So the values here, if you look at our x values for cotangent inverse, it goes from negative infinity to positive infinity. So that's why the domain is negative to positive infinity. And then when you look at the range, the y values go from 0 to pi, and notice that this is parentheses. We don't include 0 and pi in the range because that's where we have our asymptotes. So you could see our 0, and then we have our pi, and that's where our y values are between with our cotangent inverse. When we look at our secant inverse or arc secant, it's got this weird domain. and range. And that's just because there's an asymptote in the middle of the domain and range, so it kind of splits it up into two pieces. When you look at the graph of secant and cosecant, remember they're just really odd graphs with a bunch of U's and a bunch of N's with a lot of asymptotes. So to split it up so that we get all the values without repeats, this is what it's going to look like, the graph. We have an asymptote for secant inverse right in the middle here at pi over 2. And then we have graphs that have x values from negative infinity to this 1, negative 1, sorry, and then positive 1 to positive infinity. So that would be our domain, which is negative infinity to negative 1, and it includes the negative 1, and then 1 to infinity, including 1. But then the range, the y values that it gets back out are going to be from 0 to pi over 2. And then pi over 2 to pi. At pi over 2, we have that asymptote, so it's going to split our range into two pieces. So everything from 0 to pi, just not the pi over 2. And now when we look at the inverse cosecant or cosecant inverse, arc cosecant, kind of does the same thing that secant did. We're going to have an asymptote here. This time our asymptote is the x-axis. And then when we look at our values for x, we have negative infinity, to negative 1, including negative 1. And then we start at positive 1 and we go to positive infinity, which is why the domain goes from negative infinity, same domain as secant inverse, to negative 1, and then 1 to infinity, and it includes negative 1 and 1. But again, the range, similar to inverse secant, is split up because of that asymptote at 0. So it goes from negative pi over 2 to pi over 2. We just don't include the 0, which is why it's split up into these two intervals. So again, nothing you have to memorize, but you should be able to refer back to those domains and range and be able to use them. Let's just do a few examples here. So if I wanted to find the exact value for y equal to cotangent inverse of 0, I would switch it to cotangent, cotangent of y equal to 0. And now remember, similar to tangent, cotangent's a fraction. It's going to be cosine of y over sine of y. That's going to be equal to 0. So in a fraction, whenever a fraction is equal to 0, that means the numerator is 0. Or you can look at this as multiplying both sides of the equation by sine of y to get rid of the fraction, and you'll end up with cosine of y is equal to 0. So this just means I set my numerator equal to 0. So cosine is 0 when y is, the first time would be at y equal to pi over 2. And then do I have to go any further with this? Well, let's go back to cotangent inverse. Its range is from 0 to pi. And we had pi over 2, which is within the range. So I can stop there. I don't have to list any more values where cosine is 0. But if we did list more, it would be, remember, the next one would be at 3 pi over 2. But that's outside of the range, so I can stop at pi over 2. Secant inverse of 1, that's the same as secant of y equal to 1. So remember, the reciprocal of secant is cosine. So secant is the same as 1 over cosine. And the only way that's going to be equal to 1 is if cosine of y is equal to 1. If you look at it as multiplying both sides by cosine, you would get cosine of y is equal to 1. So when is cosine equal to 1? Well, the first time would be at 0, and then at 2 pi, or you could say negative 2 pi. But this is secant inverse. When you look at secant inverse, the range For secant inverse, our values from 0 to pi over 2, pi over 2 to pi, not including pi over 2. So we had the value 0, and 0 is here. It's included. So we could have stopped once we hit 0. That is in the range of secant inverse. The other ones won't work. And our last one, cosecant of -1, or cosecant of negative, cosecant inverse of 2 is the same as cosecant of y equal to 2. So remember, cosecant, the reciprocal is sine. So if cosecant is 2 over 1, then sine is 1 over 2. So you can just flip everything and have sine of y equal to 1 over 2, or you could write cosecant as 1 over sine equal to 2, or 2 over 1. And then when you solve for sine, you will eventually get to sine of y is equal to 1 over 2. So when is sine equal to half? That would be at pi over 6. That's where we first see that. It's also equal to positive half in quadrant 2 at 5 pi over 6. But remember, we're looking at things in the range of cosecant inverse. So cosecant inverse, negative pi over 2 to positive pi over 2, not including 0. So pi over 6 is within this range. It's in the 0 to pi over 2 piece. So pi over 6. So let's just remind ourselves that whenever we're solving for an inverse trig function, what we're actually doing is finding an angle. And angles can be written in radians or in degrees. So far we've just been working in radians, but we can also work in degrees. In example 7, if we're looking at cosine inverse of -1/2, remember cosine inverse is going to give us some value, and that value is actually an angle, a theta value. So I would solve this by saying cosine of theta equal to -1/2. So cosine inverse is going to give us values back in quadrants 1 and 2. And since we're looking at -1/2, we're looking at a value in quadrant 2. So cosine of theta is equal to -1/2 when theta is equal to, that would be 2 pi over 3, I believe. That would be the theta value in quadrant 2. So remember, the range here is going to be from 0 to pi. 2 pi over 3, it falls within that range. But let's say we want to write this in terms of degrees. That would give us theta equal to 120 degrees. If you don't remember how to do that, remember you're just multiplying your radians by 180 over pi to do the conversion. Let's do that again. In example B, we have theta is equal to arc sine, which is just sine inverse, of negative square root 2 over 2. So when we're dealing with sine inverse, we're looking at quadrant 1, quadrant 4. Since this is negative, we're looking at quadrant 4 in terms of negative values. If I were to rewrite this, arc sine would become sine of theta equal to negative square root 2 over 2, which means that theta is going to be equal to, in quadrant 4, that's going to be 7 pi over 4. However, that's a positive value. We need the negative value. So that's actually a negative pi over 4. That would be in terms of radians. If I want to write that in terms of degrees, I would multiply by 180 over pi, and it's still going to be negative. So our theta is going to be equal to a negative 45 degrees. All right, last one. Theta equal to sine inverse of -3 is the same as saying sine of theta is equal to -3. So when is sine equal to -3? Never. So always keep in mind that sometimes there is no solution. Sometimes values don't exist. So we would write does not exist. And in calculus, we simply write DNE for does not exist. So just keep in mind that that can happen. Our last examples, we're going to have to do something a little bit more. And now we're still not using a calculator. In example 8, it says gives the exact value if it exists. Do not use a calculator. So this first example, in example A, is sine of cosine inverse of 1/4. So there's a few things that are bothering me here. One is that I have a mixture of sine and cosine inverse. So it's not cosine inverse. And the other thing that's bothering me is the 1/4. That's not a value I recognize. If it was 1/2 or square root 2/2 or 0 and so on, I would recognize those values, but I don't recognize 1/4. So what we're going to do is we're going to do a substitution on the cosine inverse, because that's actually what's bothering me, is this cosine inverse of 1/4. So when you do your substitution, you can pick any variable you want. Maybe I'll just pick theta. Oop. And I'm going to let theta equal this cosine inverse of 1/4. So now if I were to rewrite this expression, it's going to be sine of theta. So that's what I have to find. So what I'm going to do is I'm going to go back to this theta equal to cosine inverse of 1/4, and I'm going to rewrite this as cosine of theta equal to 1/4. So I'm going to rewrite it so that it's something that I recognize. And now what I'm going to do is I'm going to drop a right triangle for cosine of theta equal to 1/4, because remember, cosine is the adjacent over the hypotenuse. And then I can figure out what sine of theta is. When I drop my right triangle, and now its cosine is positive, so I'll remember we start out with cosine inverse, which is going to be quadrant 1 and 2, but since we're looking at positive, it's quadrant 1. So when I draw my right triangle, I'm actually going to draw it in the quadrant. You don't have to. You can just drop a random right triangle. But I want to make sure I get the proper positive and negative values, so I don't have to think about that. So with respect to theta, cosine is adjacent over hypotenuse. Now this side is a positive one because it's on the positive x-axis. The hypotenuse is always positive because you can think of it as a radius out. It'll always be a positive value. And now if I find this missing side, this value, it's going to correspond to a positive y value, so that will be positive as well. So this would be using our Pythagorean formula. It's going to be some y value, where y squared plus 1 squared is going to be equal to 4 squared. So our y squared is going to be 16 minus 1, or 15, which means y is going to be the square root of 15. Now I'm not going to put the plus minus because I already know it's positive. It's in quadrant 1. So now going back to this expression, remember we let theta equal the cosine inverse of 1/4. So this expression is going to be sine of theta, and then looking at my right triangle, sine is opposite, so square root of 15 over hypotenuse, which is 4. So that was a lot of work. And the reason why it was a lot of work is because of that 1/4. It's not a value I recognize. So without a calculator, I'm kind of stuck. Let's try this again in example B. Again, notice that the sign inverse on the inside is -5/13, which is not a value that I recognize. So I'm going to do a temporary substitution for the sign inverse. I'm going to let this be, I'll use a different variable. Let me do A. So I'm going to let A equal to sign inverse of -5/13, which means that sine of A is equal to -5/13. So when we're talking about our inverse sine function, we're looking at quadrant 1 or quadrant 4. Since this is negative, I'm looking at quadrant 4. So if I'm going to drop a right triangle, it's going to be in quadrant 4. So some distance out, draw your right triangle, just random, sad right triangle. So remember, sine is opposite of A. So it's going to be opposite, which would be 5, over hypotenuse, which is 13. Now the hypotenuse is that distance out like a radius. It's always positive. So the negative has to be on the 5. So this has to be a -5, which makes sense because it's that y value. And the y value here is negative. So all I have to do now is find my remaining side using the Pythagorean formula. And this is going to be some x value. So x squared plus -5 squared is going to be equal to 13 squared. X squared is equal to, that's going to be 169 minus 25. Oops, that's a weird 25. So x squared is equal to 144, which would mean x is equal to the square root of 144. Oh, I'm just going to write 12. So x is equal to a positive 12 because it's on the positive x-axis. So now that I have my triangle, I can rewrite this tangent as tangent of A. Tangent is opposite over adjacent. Opposite of my angle is the -5. And adjacent is the x value of 12. So again, we would use this method if we were solving and we had values that we didn't recognize. So in this case, it was the 1/4 and the -5/13. So let's do something a little bit more challenging. Let's go ahead and use identities this time. In example 9a, we have cosine of 2 times sine inverse of 1/4. So a couple things that are bothering me here. The 1/4, that's not a value that I know, and I'm not supposed to use a calculator, and that 2 in front of the sine inverse. So I'm going to do a substitution as we did in the prior ones for the sine inverse of 1/4. I'm going to ignore the 2. Substitution is just going to be on sine inverse of 1/4 because that's what's irritating me the most right now. So if I I'll use A, equal to sine inverse of 1/4, that tells me that sine of A is equal to 1/4. But that also tells me that I could rewrite this cosine as cosine of 2A. And I can use an identity. I have sine of A is equal to 1/4. So remember the double angle or double number identity with cosine? You had 3 choices. You had a cosine squared minus sine squared. you had 2 cosine squared minus 1, but you also had 1 minus 2 sine squared. So I think I'm going to use 1 minus 2 sine squared of A. And the reason why is because I know what sine of A is. It's 1/4. So right away I can do 1 minus 2 times 1/4 squared, which is 1 minus 2 times 1 over 16. So 2 over 16 becomes 1/8. 1 minus 1/8 is going to be 7 over 8. If you used one of the other two formulas for cosine of 2a, then you would have to figure out what cosine of a is. So in that case, you could drop a right triangle, figure out what cosine of a is, and then use one of those other two. But why work harder than you have to? Let's look at B. This is probably the most difficult type of problem because we have an addition of two different inverse functions, and the values 3 over 5 and 5 over 13, those are values that I don't recognize. But since these are two different inverse functions, I have to do two different substitutions. So I'm just going to do an A and a B. I'm going to let A equal to sine inverse of the 3/5. And I'm going to let B equal to cosine inverse of 5 over 13. So that means that sine of A is equal to 3 over 5, and cosine of B is equal to 5 over 13. Now when we look at our initial expression, this cosine, this becomes cosine of A plus B. It becomes the addition formula for cosine. So the identity is going to be cosine of A, cosine of B, plus goes to minus sine of A and sine of B. So do I have any of those values? And the answer is yes. I have sine of A and I have cosine of B. So cosine of B is 5 over 13, but I don't have cosine of A. Minus sine of A is 3 over 5, but I don't have sine of B. So I have two different angles. I have angle A and I have angle B, which means I need two triangles. So now if I look at sine of A equal to 3/5, it's positive. So we're looking at quadrant 1. Some distance out, drop a right triangle. This is A. I'm actually just going to write A. So with respect to angle A, remember this was opposite over hypotenuse. So opposite is 3, hypotenuse is 5. Now when you do 5 squared minus 3 squared, or 25 minus 9, you're going to get 16 square rooted, you get 4. So you can do the math to figure out the remaining side, and it's positive because we're in quadrant 1. So I do have A, which means I get, so remember this was sine of A. What I was trying to find is cosine of A. And cosine is adjacent over hypotenuse, so that would be 4 over 5. If we go back to our expression, I can now replace cosine of A with 4/5 minus 3/5 times, I still don't have sine of B. I need another right triangle. So we're going to go to cosine of B equal to a positive 5 over 13. So since it's positive, this is quadrant 1. Distance out, right triangle. So cosine is adjacent. Oh, this is definitely not to scale. Adjacent is 5, opposite is, or hypotenuse, sorry, is 13. So when we do 13 squared minus 5 squared, we're going to get 144. Square root would be 12. Again, this is B. That would be our angle. So that means sine, in this case, of B is going to be opposite over hypotenuse, or 12 over 13. Now I can replace sine of B with 12 over 13. I'll just do some number crunching. We have 20 over 65 minus 36 over 65, which would be 16. Negative 16 over 65. All right. I think that's the worst it's going to get, and that's it for this section.